All right, so we are now on to R. Using our regression model, predict the fuel consumption of a Boeing 777 that has a load weight of 100 tons. That looks just like one of the previous problems, right? We already predicted the fuel consumption for a plane that has a load weight of 30, right? So same thing, we just plug in 100, right? In for X, and this time we get a fuel consumption of 33. So kind of a redundant problem, or is it? Okay, so it's very easy to just not think about things, just plug and chug and render conclusions based on your model. But one of the important things, right, we have to understand assumptions of the model, which we haven't gotten to yet. But another thing is just understanding that looking at the scatter plot, we have observations of load weights between about 10 and 35. So when we wanted to predict a load weight of 30, right, we just go up to the line and we can see it's about 14. And that's perfectly fine. But there's a difference now. If you think about trying to predict that load weight of 100, well, we can't even fit it on the screen, right? Even if we were to draw this graph bigger, it's not even close to the observed data. Okay, and trying to do that is what's called extrapolation. Okay, trying to predict observations that are outside of the range of observed data. We do not have load weights anywhere close to 100. So if you were asked or tasked with predicting such a load weight, the best thing to do is not even bother plugging it into your model, but simply stating that you cannot do so based on your model. Okay, based on your model, your model is not appropriate for predicting such a value. Okay, one thing that you might be able to get away with is predicting something slightly above 35 or slightly below that 10 or what that lower bound is. Okay, provided you also include the statement that the value is slightly outside of the range of your data. Okay, so technically it's still extrapolation, right? But a very mild form of it, right? But also as long as you're including that statement, you're right. You're putting that warning label that you can't be 100% sure that the model is appropriate for that value that's slightly outside of the range of your data. But for values far outside of the range, there's no point in even giving them, right? You should just immediately state that the model cannot predict that value accurately, right, to the best of your knowledge. Because when you start trying to predict outside of the range of your data, things can change. The entire, right, we have this nice positive relationship between the two variables, but maybe for larger and larger load weights, this pattern starts to change. Maybe it starts to shift, right? Maybe it starts to flatten out or even go down. Maybe it does, maybe it doesn't. We have no way of knowing. And another thing is maybe this plane cannot even fly when it has such a heavy load weight of 100 tons, right? It might not even be able to get off the ground. Okay, so it might not even make sense at all to even think about predicting this value. Okay, so again, these are the reasons that we don't ever want to do extrapolation. It's a very bad thing. Okay, model is only appropriate for predicting within the range of observed data. Okay. Next, S, calculate the correlation, R, between fuel consumption and load weight. Okay, this is a topic which we have not covered to this point, so we are going to go ahead and talk about it right now. So the correlation coefficient, which denoted lowercase r, it describes the strength of the linear relationship between two variables. Notice I am capitalizing linear. That is a very important term in this sentence. A linear relationship. Okay, linear just being straight line, right? Straight line. No strange pattern. Just straight line. The correlation must fall between -1 and 1. Including those values is fine. up to and including -1 and 1. So I want to give you some descriptions of ranges of values and how you might interpret their relative strength, okay? And also the direction, which is fairly obvious, but so these are by no means the standard. Unfortunately, with a lot of things in statistics, there is some subjectivity. Okay, so for example, this might be -1 to say -0.6 or something, or -0.8, but this gives you a rough idea. Okay, so I would call something from -1 to -0.6, or sorry, -0.7, a strong negative relationship. Okay, negative kind of obviously because the numbers are negative, and strong because it is on the low end toward -1. Okay, so don't let that fool you as to thinking it's weak. The closer you are to -1 or the closer you are to 1, it becomes stronger. Okay, the closer to 0 we get, it becomes weaker. So from -0.7 and -0.4, and now I might consider that a moderate negative relationship. Again, negative just because it's negative, and the values, the absolute values, kind of determining that it's moderate. Now, maybe from about -0.4 to 0, we can call that a weak negative relationship. Okay? And the one thing to always keep in mind, I am stating strong and negative, right? So I'm describing the strength, I'm describing the direction, right? Negative being the direction, strong, moderate, weak being the strength, but it all must always include in your description the bolded word linear. Okay, that is the most important word because it is it's describing the strength of the straight line relationship. Okay, so continuing on, once we go from 0 to 0.4, it's going to be a weak positive relationship, right? So it's basically going to be a mirror image of what I already put there, but now we're just going to be putting positive everywhere. So 0.4 to 0.7, moderate positive relationship, and 0.7 to 1, going to be a strong positive relationship, okay? Now, if you have a correlation of 1, that is that would be a perfect positive relationship. If you have a correlation of -1, that would be a perfect negative relationship. And by perfect, what I mean is that all points would fall exactly on a line, right? The relationship would be deterministic, right? It would be a perfect line through every single point, okay? Now, one thing I'll say is it's very easy starting out to confuse interpreting the correlation, okay? Because it is related to the slope in one way, in that we can see clearly we have a positive slope, right? Which means that the correlation must be positive. As one goes up, the other goes up, okay? And likewise, if there was a negative slope, we would know that the correlation would be negative, a negative relationship. As one goes up, the other goes down. Okay, and if there is a horizontal line, then that would mean a slope of 0 and also a correlation of 0, meaning the two variables are not linearly related. Okay, but besides the slope being positive versus negative versus 0, okay, besides kind of just the basics of that, the slope does not relate to the strength of the correlation. Okay, only whether it's positive, 0, or negative. Okay, that determines whether the correlation is negative, positive, or 0, not correlated. So, for example, if you take this exact graph, okay, no, so here so if you take this exact graph and you just think about shifting all of the points, okay, shifting all the points and just kind of tilting the graph such that the graph has a steeper slope, okay, but everything else and all the points are the same, just tilt the graph up or down a little bit. The correlation would be the exact same, Okay, so the slope, it doesn't matter whether the slope is really steep or not very steep. If the points are scattered in this exact same way, just tilted up or down, the correlation is the exact same. Okay, the magnitude of the slope does not affect the magnitude of the correlation. Okay, what affects the magnitude of the correlation are how tightly these points are scattered about the line. So for example, I would probably consider this graph to be a weak, possibly moderate correlation, of course positive. But how we could increase it is if you think about taking all of those points and shifting them closer and closer to the line, but keep this exact same slope of points, just smush them closer and closer to the line. That's what increases the correlation. Okay, how tightly the points fit about a straight line. That is what impacts the correlation. So if you just smush those points closer and closer to that line, that would increase the correlation closer and closer to 1, such that if you finally smushed all points onto exactly that red line, then there would be a correlation of 1. Okay? But tilting the graph up or down does not affect the strength of the correlation. Okay? Again, the only relation between the slope is whether it's positive, negative, or 0. But besides that, it doesn't matter whether you say have a slope of 0.1 or a slope of 100. Okay? Doesn't matter how shifted up or down that line is, it does not affect the strength of the correlation. Okay? And again, I would guess a weak, possibly moderate correlation. And so it's very easy to calculate the correlation. All we have to do is put core and then put x comma y, in this case load comma fuel. And so in this case we can see it's 0.55. Of course that is a positive value because the slope is positive. If the slope was negative, that would be a negative correlation. Okay? But in this case I would interpret that as a moderate, positive, linear relationship. Never leave out that word linear. Okay? That is a very, very key word. So as pretty much as I was just saying, there appears to be a moderate positive linear relationship between fuel consumption and load weight. So it's possible for two variables to have to be very related in ways that are not linear, right? So for example, all points could be close to some parabola, okay? Or some upside down U. Maybe the points go up and then back down, right? And there might be some real clear pattern of the data. But if, for example, the points fall on kind of like an upside down U, they go up and then back down, they could have that nice clear relationship, but the correlation would still be 0. Because an upside down U, right, that curvature, that is not a linear pattern, a straight line pattern. Okay, so don't let that fool you. If you have some nice clear pattern in the data that is very curved, for example, it's still possible to have a very low or even 0 correlation between the two variables, because correlation only describes the strength of the linear relationship. Okay, that straight line relationship. So one of the things that I want to briefly bring up is a little graph like this: ice cream sales versus drowning deaths. And it's pretty clear to see from this graph, real data, that as ice cream sales goes up, drowning deaths go up, right? So there is a clear positive correlation between these two values, right? A straight line appears to fit this data well. So there's a clear positive, I would probably call it, based on these kind of how far away these points are, moderate, probably even strong linear relationship between ice cream and drowning deaths. So that means that we should stop selling ice cream, right? Because ice cream is causing more drowning deaths. Well, of course not, right? I'm sure everybody has heard this cheesy term before, correlation does not imply causation, okay? So just because these two are related does not mean that one is causing the other, okay? So I think pretty clearly drowning deaths, when are people drown, or how are people drowning? They're drowning in the water, right? They're swimming. And when do people swim? They swim in the summertime when it's nice and hot. And when do people buy ice cream? In the summertime when it's nice and hot. Okay, so clearly there is the fact that it's hotter weather is causing both of these to increase, but by no means is one causing the other. Okay, so just something to keep in the back of your mind. Probably already knew it, but okay. Down to number T. Oh well, that's pretty much it, right? We already described the strength and direction of the linear relationship. Okay. So that's a very good example of pretty much everything I could ask you except the assumptions on epsilon, right? We have a specific set of assumptions on that error term, right? These 4 assumptions, and we did not verify them, did we? No, we did not. Okay, and of course, as with everything else, if you have no idea whether your assumptions are correct or not, then you have no idea whether the model that you just created and made inference about is worth anything or not, right? Everything that we just did could be complete BS if those assumptions are violated. And we will get to that maybe next time, or certainly next week, as to how you can verify those assumptions. And also what's next is this problem number 6, which gets into multiple linear regression, okay?